You walk into a palace hall in Samos around 530 BCE. Square tiles stretch across the floor, white stone, black stone, a pattern older than memory. You're waiting for the tyrant Polycrates and you're bored. Your eyes drift down. One square, another. A diagonal cuts through. Two triangles appear where one square lived. Something shifts in your mind. The diagonal measures longer than the side. How much longer? You stare at these tiles and suddenly the universe cracks open. This is how legends say Pythagoras discovered his theorem. But here's what nobody tells you. He wasn't the first, not even close. And the mental process he went through to understand this relationship, it will shatter everything you think you know about how knowledge works. Before we dive in, if you value documented mathematical history like this, subscribe. It's the best way to support our work. Also comment from which city you're hearing this from. This script is researched and factual, using sources from the Yale Babylonian Collection Tablet, YBC 7289, dating between 1800 and 1600 BCE, and peer-reviewed studies from Historia Mathematica Volume 25, published in 1998 by D. H. Fowler and E. Ars Robson, examining how ancient civilizations computed square roots. These aren't Wikipedia summaries, these are clay tablets you can hold. Mathematical treatises with cuneiform marks that predate Pythagoras by over 1,000 years. Now back to the information. The year is 1800 BCE, Mesopotamia, southern Iraq. A student sits in a scribal school, clay tablet in hand. His teacher gives him a problem. A square? Side length 30. Find the diagonal. The student presses his stylus into wet clay. He draws the square, both diagonals. Then he writes numbers. 1, 24, 51, 10 in base 60 notation. This number is the square root of 2, accurate to 6 decimal places. The greatest computational precision achieved anywhere in the ancient world. The tablet survives. It sits in Yale today. Catalog number YBC 7289. You can see it. The Babylonians knew the theorem 1,000 years before Pythagoras was born. Egypt, 1600 BCE. Construction workers on the Nile. They need right angles, perfect corners for temples and tombs. They take a rope, 12 knots, equally spaced. They form a triangle, 3 units on one side, 4 on another, 5 on the third. The angle where 3 meets 4, exactly 90 degrees. Every time. They don't write equations, they don't prove theorems, they build. The 3, 4, 5 triangle appears in hieroglyphics, in foundation deposits, in the actual corners of pyramids that still stand. The Egyptians used the relationship. They applied it. Whether they understood why remains unclear. India, 800 to 400 BCE. The Baudhayana Sulba Sutra, a text on altar construction, verse after verse describing rope geometry. One verse states it clearly. In a rectangle, the diagonal produces what the two sides produce separately. The language isn't algebraic, it's practical, but the mathematics is exact. The text includes Pythagorean triples, lists of whole numbers that satisfy the relationship, 3, 4, 5, 5, 12, 13, 8, 15, 17. The Indians didn't just know one case, they systematically explored the pattern. China, 1000 BCE or earlier, the Zhoubi Suan Jing, a mathematical classic. It contains a diagram called the gugu, a square rotated inside another square. 4 identical triangles arranged around the center. The proof is visual, immediate. Move the triangles. The areas match. The relationship emerges not from calculation, but from pure spatial reasoning. The Chinese proved it geometrically, centuries before any Greek wrote anything down. So where does that leave Pythagoras? Born around 570 BCE on the island of Samos, son of Minosarchus, a gem engraver. The historical record on him is thin, desperately thin. He wrote nothing, not one word survives in his own hand. Everything we know comes from followers who wrote centuries later. Iamblichus wrote in the 3rd century CE. That's 700 years after Pythagoras died. Porphyry, Diogenes Laertius, all of them writing from legend mixed with fragments. The man himself is smoke. But the legend is concrete, and that legend tells us something about the mental process. Around 530 BCE, Pythagoras leaves Samos. Some sources say he fled the tyrant Polycrates. Others say he left to find wisdom. He travels Egypt first. Captured by Persian forces under Cambyses II in 525 BCE. Taken to Babylon as prisoner. Released eventually. Maybe visits India. The timeline is contested, but the pattern is clear. He collects knowledge. Egyptian rope geometry. Babylonian computational methods. Eastern philosophical systems. He arrives in Croton in southern Italy around 530 BCE. A Greek colony, wealthy, cultured. He's 40 years old. He founds a school, not a school like you're imagining, a religious community, a philosophical brotherhood, the Pythagoreans. They take vows of secrecy, share all property, follow strict rules, vegetarianism, periods of silence, abstinence from beans for reasons still debated. They believe in transmigration of souls, that when you die, your soul enters a new body, human or animal. This isn't just mathematics. This is mysticism wrapped around numbers. To the Pythagoreans, numbers are sacred. Numbers are divine. Everything in the universe reduces to numerical relationships. Music, astronomy, ethics, all of it flows from numbers and their ratios. Here's where the palace tile story enters. Multiple ancient sources place it. Pythagoras, waiting in a palace hall, probably Polycrates. Pallas, back in Samos before he left, square tiles on the floor. He stares at them. The legend says he noticed that when you divide a square diagonally, you get two right triangles. The two shorter sides of each triangle are equal. Both are sides of the original square, the longer side, the diagonal, the hypotenuse. He sees it visually first, one square sitting on the diagonal. Its area equals two original squares, the squares on the two legs. A squared plus a squared equals the diagonal squared. For an isosceles right triangle, this relationship jumps out from the geometry. The area proof is obvious, just count tiles. But Pythagoras doesn't stop there. This is where the mental process becomes profound. He makes a leap. What about triangles where the legs aren't equal? What if one leg is 3 units and the other is 4? Does the relationship still hold? The tiles can't show him that. The Egyptian rope workers knew 3 squared plus 4 squared equals 5 squared, 9 plus 16 equals 25. But knowing a specific case and understanding the general principle, those are different universes. Pythagoras moves from observation to generalization, from specific tiles to universal truth. This is the shift from craft knowledge to mathematical proof, the proof itself. We don't know what Pythagoras actually did. He left no record. The first complete proof that survives comes from Euclid's Elements. Book 1. Proposition 47, written around 300 BCE. That's 230 years after Pythagoras died. Euclid's proof is geometric. Intricate. It constructs squares on all 3 sides of a right triangle, and then proves, through a series of area arguments, that the square on the hypotenuse equals the sum of the squares on the 2 legs. The proof depends on previous propositions, on the theory of parallel lines, on congruence of triangles. It's a masterwork of logical architecture. Sir Thomas Heath, the great historian of Greek mathematics, suggests Pythagoras might have used a different proof, a simpler one, based on similarity of triangles. Drop a perpendicular from the right angle to the hypotenuse. This creates 3 similar triangles, the original and 2 smaller ones. The ratios between corresponding sides must be equal. From those ratios, the Pythagorean relationship follows algebraically. But this proof requires the theory of proportions. That theory wasn't fully developed until Eudoxus, 2 centuries after Pythagoras, so maybe Pythagoras didn't use it, maybe he did but kept it simple, or maybe he never proved it at all. Here's what makes sense from the palace tile moment. Pythagoras sees the pattern visually. He understands it spatially. For the isosceles case, it's immediate. 1 square on the diagonal fits exactly 2 squares on the legs. Then comes inductive reasoning. He knows the Egyptians use 3, 4, 5 triangles. He can verify that case. 3 squared is 9. 4 squared is 16. 5 squared is 25. 9 plus 16 equals 25. It works. He probably tests other triples. 5, 12, 13. Check. 8, 15, 17. Check. Each verification strengthens the pattern. The relationship holds for every right triangle he examines. At some point, accumulated evidence becomes conviction. This isn't just coincidence, this is mathematical truth. But conviction and proof diverge here. Ancient mathematicians didn't always distinguish between strong empirical evidence and logical necessity. The Babylonians computed square root of 2 to 6 decimal places. They clearly understood the relationship. But did they prove it in the Greek sense? Probably not. They verified. They calculated. They applied. The Greeks demanded something more. Demonstration. Starting from axioms, building through logic, arriving at conclusions that must be true. That shift in thinking, that's what we attribute to the Pythagoreans. Not discovering the relationship. Babylonians beat them by a millennium, but formalizing the idea of mathematical proof. Let's get specific about what mental tools that assistant Pythagoras had available. Geometric visualization, the ability to see relationships between shapes, pattern recognition, noticing that the same relationship appears across different triangles. Proportional reasoning, understanding that ratios can express relationships, numerical verification, computing squares and checking sums, and finally, the concept of generality. Moving from many examples to one universal statement, these aren't trivial skills. Each one requires training, development, practice. Pythagoras spent years collecting this toolkit. Egypt taught him practical geometry. Babylon taught him computation. Eastern philosophy taught him to seek underlying unity. He synthesizes these traditions into something new. The Pythagorean Brotherhood becomes a knowledge factory. Members share discoveries. They work collectively. When someone proves something new, it gets attributed to Pythagoras, the master. They don't say, Hippasus proved this. They say the master proved this, or simply it was proved. This communal attribution makes it impossible to untangle what Pythagoras himself discovered versus what his school developed. Most historians now think the theorem's proof came after Pythagoras died. His followers, building on his ideas, formalized the demonstration. But the core insight, the pattern recognition, the leap from tiles to triangles, that mental process likely happened in that moment in the palace hall. Now the story takes a dark turn. Numbers are divine to the Pythagoreans, specifically rational numbers. Numbers you can express as ratios of whole numbers, 1/2, 3/4, 7/9. Every number, they believe, is a ratio. The universe is ratio, harmony, proportion, order. This belief is foundational, religious, non-negotiable. Then someone in the Brotherhood discovers something terrifying. The square root of 2, the diagonal of a unit square. It cannot be expressed as a ratio. No matter how hard you try, no fraction equals it. The proof is simple but devastating. Assume square root of 2 equals some fraction in lowest terms. Square both sides. Both numerator and denominator must be even, but that contradicts lowest terms. Therefore, square root of 2 is irrational. It exists outside the system of ratios. It doesn't fit their universe. The discoverer? Tradition names Hippasus of Metapontum, a Pythagorean alive in the late 5th century BCE. The sources on what happened are confused, contradictory. One version says he discovered irrationals. Another says he revealed how to construct a dodecahedron inside a sphere. Both violations apparently worthy of death. Iamblichus, writing in the 3rd century CE, says Hippasus drowned at sea. Divine punishment for revealing secrets. Or maybe his fellow Pythagoreans threw him overboard. Pappus of Alexandria says whoever first divulged the secret of irrationals perished in water. The details shift between accounts. What's consistent? Hippasus died. The Pythagoreans suppressed his discovery. They tried to keep irrational numbers secret. Modern historians doubt the drowning story. It's too neat, too dramatic, too much like morality tale. What probably happened? Hippasus made a discovery that contradicted Pythagorean doctrine. The Brotherhood expelled him. He died later, maybe accidentally at sea. Followers turned his death into divine retribution, a warning against revealing sacred knowledge. But the mathematics couldn't be suppressed. Once you see that square root of 2 is irrational, you can't unsee it. The proof is too simple, too clear. Other mathematicians independently discovered it. The secret leaked, the Pythagorean worldview fractured. This is where Pythagoras' mental process reveals something deeper about how we understand reality. He looked at tiles and saw a pattern, universal, eternal, true. But that pattern contained within it the seed of its own destruction. The diagonal of the square, the simplest application of his own theorem, produces a number that can't be expressed in the terms his system allows. His greatest discovery carried the proof that his philosophy was incomplete. He couldn't have known this standing in that palace hall. The irony is almost unbearable. If you value this kind of deep documented history, subscribe. It's the best way to support our work. Also comment from which city you're hearing this from. The sources here include Wikipedia's entry on Hippasus, updated September 11th, 2025, citing Iamblichus and Pappus directly. And peer-reviewed research from Scientific American, published June 13th, 2024, titled How a Secret Society Discovered Irrational Numbers, Examining the Historical Evidence. These aren't legends passed down orally. These are texts, clay tablets, papyri, direct evidence from antiquity. Now back to the information. Let's trace what Pythagoras actually contributed versus what got attributed to him. The theorem, known to Babylonians by 1800 BCE, tablet YBC 7289 proves this, the 3-4-5 triangle. Egyptians used it for pyramid construction by 2500 BCE. Foundation deposits confirm this. Lists of Pythagorean triples. Indian Sulba Sutras contain them by 800 BCE. Geometric proof, possibly Chinese by 1000 BCE. So what did Pythagoras do? He synthesized. He formalized. He possibly created the first rigorous proof that satisfied the Greek standard of demonstration. He built a school that turned mathematics into a systematic discipline. He inspired generations of thinkers. Plato studied Pythagorean ideas. Aristotle wrote about them. Euclid codified them. The political situation matters too. Croton, around 500 BCE. The Pythagoreans gain influence. They advise the ruling council. They shape policy. Then Croton goes to war with neighboring Sybaris. 510 BCE. Croton wins decisively. Destroys Sybaris completely. The victory creates tension. Some citizens want democracy. The Pythagoreans oppose it. They believe in rule by the wise, the educated elite. This makes them enemies. Around 500 BCE, or shortly after, violence erupts. Pythagorean meeting houses burn. Members are killed. Some reports say over 50 Pythagoreans die in Croton alone. Pythagoras himself flees to Metapontum, another Italian colony. He dies there, maybe murdered, maybe of natural causes. The sources disagree, but his school survives him, scattered, underground. The ideas persist. Here's what the mental process reveals about mathematical discovery generally. First, pattern recognition, seeing relationships that others miss. Second, generalization, moving from specific to universal. Third, verification, testing the pattern against examples. Fourth, proof construction, building logical arguments that demonstrate necessity. Fifth, synthesis, combining knowledge from different traditions. Pythagoras, or his school, excelled at all five. They took Egyptian practical geometry, Babylonian computational skill, and Greek logical rigor, then forged them into something unprecedented. A mathematics based on proof. The theorem itself becomes foundational. Every right triangle in existence satisfies the relationship. The square of the hypotenuse equals the sum of the squares of the two legs. This isn't just theoretical, it's practical. Architects use it, surveyors use it, navigators use it. You need to find distance, Pythagorean theorem. You need to check if an angle is 90 degrees, Pythagorean theorem. You need to calculate forces in physics, Pythagorean theorem. The relationship appears in trigonometry, in coordinate geometry, in vector mathematics, in quantum mechanics. Everywhere you look in mathematics, this pattern emerges, and it all traces back to that moment when a man looked at floor tiles and saw something universal. But let's be precise about what seeing something universal means. Pythagoras didn't invent the relationship. Nature did, or mathematics did, or God did, depending on your philosophy. The relationship exists independent of human observation. Right triangles satisfied the theorem before humans existed, before Earth existed, before the universe existed, if mathematical truths are eternal. What Pythagoras did was recognize it, name it, formalize it, turn implicit truth into explicit knowledge. That's the mental process. Not creation, recognition. He saw what was always there. The 3, 4, 5 triangle shows this beautifully. Egyptian rope workers used it. They knew empirically that when you make a triangle with sides 3, 4, 5, the angle opposite the 5 is 90 degrees. They tested it. It worked. They used it to lay foundations. But did they know why? Did they understand that 3 squared plus 4 squared equals 5 squared? That 9 plus 16 equals 25? That this relationship determines the right angle? The evidence suggests not they had the method, not the explanation. Pythagoras provided the explanation. He showed why it works. He connected the practical knowledge to the underlying mathematical structure. This distinction between knowing how and knowing why is central to the history of mathematics. Babylonians could compute square roots iteratively. Start with a guess. Divide the target number by the guess. Average the result with the original guess. Repeat. This method converges rapidly to the correct answer. For a square root of 2, start with 1.4. Divide 2 by 1.4. Get 1.428. Average them. Get 1.414. Divide again. The accuracy increases with each iteration. Babylonians clearly knew this method. Tablet YBC 7289 shows they used it, but did they prove it must converge? Did they demonstrate why it works? Probably not. They had the algorithm. They didn't have the theory. Greek mathematics shifts the focus. Algorithm to theory, practice to proof. Euclid's Elements epitomizes this. 300 BCE, 13 books. 465 propositions, starting from definitions and axioms, building through logical deduction, proving each result before using it to prove the next. Book 1, proposition. 47 proves the Pythagorean theorem. But to get there, Euclid first proves, proposition 46, how to construct a square on a given line. Before that, proposition 31, how to draw parallel lines. Before that, proposition 4, triangle congruence. The architecture is deliberate, careful. Nothing is assumed. Everything is demonstrated. Proclus, writing in the 5th century CE, comments on Proposition 47. He says some attribute the theorem to Pythagoras. He mentions the ox sacrifice story. Pythagoras supposedly sacrificed an ox upon discovering the theorem. Proclus notes, this contradicts other reports that Pythagoras was vegetarian. He's skeptical, as he should be. The historical evidence is thin. What Proclus does confirm is that the theorem was called Pythagorean by his time. The attribution was standard, whether deserved or not. The mental process we're trying to reconstruct then has these components. Visual observation. Pythagoras sees tiles arranged in patterns. Diagonal relationships. Spatial reasoning. He imagines triangles within squares, areas and proportions. Numerical verification. He tests specific cases. 3, 4, 5, 12, 13. Pattern recognition. He notices the relationship holds universally. Generalization. He formulates the principle for all right triangles, and potentially proof construction. He builds a logical argument demonstrating necessity. Each step requires different cognitive tools: visualization, calculation, abstraction, logic. The integration of these tools constitutes mathematical thinking at its highest level. Modern research in mathematics education studies this process. How do students learn the Pythagorean theorem? Most start with the formula. A squared plus b squared equals c squared. They memorize it, apply it to problems, but do they understand why it's true? Studies show most don't. They can calculate, they can't explain. The proof remains mysterious. Even Euclid's proof, though rigorous, doesn't necessarily build intuition. You follow the steps, you verify each claim, you reach the conclusion, but the insight, the aha moment, that often remains elusive. Some educators use visual proofs. Rearrangement demonstrations show that the areas physically match. Others use algebraic approaches. Multiple methods exist. Over 300 distinct proofs have been published. Each offers a different path to the same truth. President James Garfield, before entering politics, published a proof in 1876, based on trapezoid area. Elegant and simple. A 12-year-old Einstein developed a proof using similarity of triangles. Leonardo da Vinci created a proof. So did Bhaskara in 12th century India. The theorem invites proof. It begs to be demonstrated. Each new proof reveals a different aspect of why the relationship must be true. This multiplicity suggests something profound about mathematical truth. There isn't one path. Many roads lead to the same destination. Pythagoras found one path. Others found hundreds more. The cognitive science of mathematical insight remains partially mysterious. How does the brain recognize patterns? What neural processes underlie abstraction? How do we move from specific examples to general principles? Neuroscience has mapped some of this. The parietal cortex processes spatial relationships. The prefrontal cortex handles abstraction and logic. The hippocampus stores memories of previous examples. Mathematical thinking requires all these regions working together. But the moment of insight? The flash when the pattern suddenly becomes clear? That remains somewhat elusive. We know it involves reconfiguring how you see the problem. A gestalt shift, the duck becomes a rabbit, the random lines become a face, the specific triangles become instances of a universal principle. Pythagoras in that palace hall experiences this shift. He's staring at tiles, bored. His mind wanders. Then suddenly the triangles aren't just triangles. They're examples of a deeper pattern. The areas relate in a specific way. Always, necessarily. This recognition is the discovery. Not the theorem itself. The theorem was always true. The discovery is seeing it, making it conscious, communicating it to others. Pythagoras walks out of that hall with a piece of knowledge that will carry his name for millennia, whether he deserves full credit or not. Let's address the controversy directly. Does Pythagoras deserve to have the theorem named after him? Arguments against. Babylonians knew it first by over 1,000 years. Egyptians applied it centuries before him. Indians, Chinese, all developed versions independently. Pythagoras may not have even proved it. His followers might have. He wrote nothing down. All evidence is secondhand. Arguments for it, he formalized it into Greek mathematics. He possibly created the first rigorous proof. He founded a school that systematized mathematical thinking. He influenced Plato and Aristotle, who shaped Western philosophy. The naming stuck. Euclid calls it Proposition 47, but later authors attribute it to Pythagoras. By Roman times, the attribution was standard. Cicero and Plutarch both reference Pythagoras and the theorem. The name persisted through medieval times, through the Renaissance, into modernity. Changing it now would cause confusion without correcting historical injustice. Some propose calling it the Gugu theorem after the Chinese, or using the Babylonian name if one existed. But tablet YBC 7289 doesn't name the relationship. It just demonstrates knowledge of it. The Egyptians didn't name it either. The Indians called it different things in different texts. Pythagoras, or his school, gave it prominence in the tradition that became dominant. European mathematics, Western science, that's not fair, perhaps, but it's historical fact. The theorem carries his name because his school, his followers, his influence shaped how mathematics developed in Greece, Rome, medieval Europe, and the modern world. What about the theorem's impact on broader thought? Enormous. The discovery or recognition that geometric relationships can be expressed numerically had vast implications. It suggested the universe is mathematical, comprehensible through reason, predictable, ordered. This idea underpins science. Galileo said the book of nature is written in the language of mathematics. He was echoing Pythagorean thought, Newton's physics, mathematical, Einstein's relativity, mathematical, quantum mechanics, mathematical. The entire scientific revolution rests on the assumption that mathematical relationships describe reality. Pythagoras didn't originate this idea alone, but his school championed it, developed it, transmitted it to future generations. The theorem also reveals something about the nature of mathematical truth. It's universal. A right triangle in Babylon satisfies the same relationship as a right triangle in Greece, China, or Mars. The truth doesn't depend on culture, language, time, or place. It's not constructed by humans, it's discovered. This philosophical point has implications for how we understand knowledge generally. Are there other universal truths? Moral truths? Logical truths? The Pythagorean theorem becomes a model for certain truth in an uncertain world. If we can prove this, what else might we prove? The mental process Pythagoras went through is therefore not just about geometry. It's about how humans grasp reality. We observe, we pattern, we abstract, we verify, we prove. This method works. It produces knowledge that lasts. The theorem has been true for over 2,000 years. It will remain true. No future discovery will overturn it. That permanence is rare. Most human knowledge is provisional. Scientific theories get revised. Historical interpretations shift. But mathematical proofs, once established, endure. The Pythagorean theorem is eternal truth captured by mortal mind. The tragedy of the irrational numbers deepens this. Pythagoras' method produced truth, but that truth contained paradox, the diagonal of the unit square. The simplest application of his theorem yields a number that can't be expressed in the terms his philosophy allows. The universe's ratio, they believed. But here's a length, a real physical length, that isn't ratio. It's irrational, infinite, non-repeating, no pattern in the decimal expansion, no fraction that captures it. The theorem that was supposed to reveal cosmic order instead revealed cosmic disorder, or a different kind of order, deeper, stranger, less comfortable. Hippasus's death, real or legendary, symbolizes this tension. New knowledge threatens old certainty. The discoverer pays the price. Science history repeats this pattern. Galileo threatened with execution for heliocentrism. Darwin attacked for evolution. Einstein initially rejected for relativity. Revolutionary truth rarely receives welcome. It disrupts, it challenges, it forces reconfiguration of worldview. Hippasus discovered something true. The Pythagoreans killed him, or expelled him, or let him drown. Truth and acceptance diverge. The mental process that leads to discovery doesn't guarantee the discovery will be celebrated. Modern education often teaches the theorem without this context. Students memorize the formula, they solve problems, find the hypotenuse, find a leg, calculate distances, but they don't learn the history, the 1,000-year development, the multiple independent discoveries, the philosophical implications, the tragic irony of irrational numbers, the political violence that killed Pythagoreans. All of that gets stripped away. What remains? A formula, useful but empty, divorced from meaning. Restoring the context transforms the theorem. It's not just a squared plus b squared equals c squared. It's a window into how humans come to know truth, how we build on previous knowledge, how different cultures contribute, how synthesis produces breakthrough, how formalization creates permanence, how discovery can threaten belief, how mathematics connects to philosophy, religion, politics. Power. The theorem becomes a story, a human story, with heroes and villains, insights and tragedies, victories and defeats. Pythagoras walks out of that palace hall. He's seen something, a pattern in the tiles, a relationship between areas. He carries this vision to Italy. He founds his school, he gathers followers, they develop the idea, prove it, apply it, build on it. They also suppress contradictory discoveries, maintain secrecy, create orthodoxy. The school eventually collapses. Violence destroys it, but the mathematics survives. It spreads. It evolves. Other mathematicians pick it up. Euclid formalizes it. Archimedes extends it. The theorem lives on, disconnected from its founder. By medieval times, Islamic mathematicians study it. Al-Khwarizmi, Omar Khayyam. They prove it in new ways, apply it to astronomy, architecture, art. European scholars encounter these texts. Fibonacci brings Islamic mathematics to Italy. The Renaissance rediscovers Greek sources. Euclid's Elements gets translated, printed, distributed. The theorem becomes standard knowledge. Every educated person learns it. Newton uses it. Descartes uses it. Fermat extends it. His last theorem asks if a to the n plus b to the n equals c to the n has integer solutions for n greater than 2. Turns out it doesn't. Took 350 years to prove. Andrew Wiles finally did it in 1993. The Pythagorean theorem inspired centuries of research. Today we teach it in middle school. Millions of students worldwide learn the formula, calculate hypotenuses, solve distance problems. Most will never think about Pythagoras, never wonder who he was, how he discovered it, what mental process he used. The theorem has become so standard, so basic, so fundamental that its origins fade. It's just there, part of the mathematical landscape, like addition or multiplication, universal, eternal, obvious. But it wasn't obvious to the Babylonian student pressing numbers into clay. It wasn't obvious to the Egyptian rope worker forming right angles. It wasn't obvious to the Indian altar builder or the Chinese geometer. Each had to discover it, recognize it, formalize it. The relationship exists independent of human minds, but human minds have to grasp it. That's the process. That's what Pythagoras did in that palace hall. He grasped it, made it conscious, started the chain that leads to us, standing here, knowing the theorem, using it, understanding why right triangles behave the way they do. The theorem reveals deep truth about space itself. Euclidean space, flat space, the space we live in at human scales. In that space, distance obeys the Pythagorean relationship. To find the distance between 2 points, you calculate the change in x squared plus the change in y squared, then take the square root. That's literally the Pythagorean theorem applied to coordinates. Descartes formalized this in the 17th century. Analytical geometry. Algebra meets geometry. The theorem bridges them. It shows they're describing the same reality from different angles. Einstein extended this special relativity, space-time. Distance in space-time isn't Euclidean. Time enters the equation. The interval squared equals space squared minus time squared. The minus sign changes everything. But the form, Pythagorean, general relativity curves this further. Space-time bends near mass. Distance becomes complicated. But locally, in small regions, the Pythagorean relationship still holds approximately. The theorem is fundamental to physics itself, to how we measure, how we describe reality mathematically. Quantum mechanics uses it too. Wave functions, Hilbert spaces, infinite dimensional spaces where quantum states live. Distance between states, defined using a generalized Pythagorean theorem, the inner product, the norm. All of it traces back to that basic relationship between sides of a right triangle. Pythagoras couldn't have imagined his tiles would lead here, to quantum computers, to general relativity, to black holes and entanglement. But the mathematics doesn't care about imagination. It follows its own logic. The theorem he recognized has implications that took 2,000 years to fully explore, and we're still exploring. The mental process, then, isn't just historical curiosity, it's methodology. How do you discover truth? You observe carefully. You notice patterns. You test hypotheses. You verify repeatedly. You abstract from specific to general. You formalize through proof. You build on previous knowledge. You synthesize across traditions. You question orthodoxy. You follow implications wherever they lead. This is the scientific method. The mathematical method, the method of reason. Pythagoras didn't invent it alone, but he exemplified it. His theorem demonstrates it, his school propagated it, Western civilization inherited it. That legacy is complex. The good, systematic mathematical thinking. Rigorous proof, universal truth. The bad, secrecy, dogmatism, violence against dissent. The Pythagoreans gave us theorems and killed Hippasus. Both are true. Both matter. We can honor the mathematics while acknowledging the human failures. We can teach the theorem while telling the full story. Context enriches rather than diminishes. Knowing Babylonians knew it first doesn't reduce Pythagoras' contribution. It shows knowledge is cumulative, collaborative across time and space. No single genius invents everything. We build on those who came before. Let's return to that palace hall one more time. Pythagoras stares at tiles, square tiles, black and white. A diagonal cuts through. Two triangles form. He sees that the diagonal's square equals two tile squares. Then he wonders, other triangles? Different sizes? Does the pattern hold? The question drives him. He tests. He verifies. He thinks. He proves or tries to prove or imagines a proof. And in that mental process, something shifts in human history. Mathematics becomes systematic. Proofs become standard. Knowledge becomes cumulative. The tiles reveal not just a theorem, but a method, a way of thinking that will shape millennia. The final piece of evidence reframes everything. In 2022, researchers at the University of New South Wales published analysis of Babylonian tablet, Psi 427, dating between 1900 and 1600 BCE. The tablet shows land survey calculations, applied geometry, but what's striking is the sophistication. The Babylonians used Pythagorean triples, 3, 4, 5, 8, 15, 17, 5, 12, 13. Not just for abstract mathematics, for practical surveying, accurate land division, they understood the relationship deeply, theoretically and practically. Over 1,000 years before Pythagoras was born, the tablet was excavated in 1894. It sat in Istanbul Archaeological Museum for over a century. Only recently did researchers fully decode its mathematical content. This changes the narrative. Pythagoras didn't discover the theorem. He inherited it, recognized it, formalized it, transmitted it. But the knowledge was ancient before he touched it. Standing in that palace hall, staring at tiles, Pythagoras experiences something real, a moment of clarity, of insight, of recognition. But he's recognizing what others knew, what the tiles themselves embody, what reality enforces. The theorem is true because space is structured a certain way. Right triangles must satisfy the relationship, not because Pythagoras said so, because geometry demands it. His contribution is seeing it clearly, expressing it precisely, proving it rigorously, creating a tradition that ensures it gets remembered. That's not nothing, that's substantial, but it's not discovering new truth, it's discovering old truth, making it new through formalization. The square on the hypotenuse equals the sum of the squares on the two legs, true in Babylon, true in Egypt, true in India, true in China, true in Greece, true on Earth, true on Mars, true everywhere in Euclidean space, true always. The mental process that leads to this recognition is reproducible, valuable, worth studying, worth honoring, worth teaching. But so is humility about what counts as discovery versus what counts as recognition. Pythagoras recognized. He formalized, he proved, he transmitted. Those are real contributions. Necessary. Important. But the theorem was true before him and would remain true without him. His genius was in seeing what was there, not in creating what wasn't. That distinction matters for how we think about all discovery. Scientific, mathematical, philosophical. We don't invent reality, we uncover it, we describe it, we formalize it. The descriptions can be creative, original, insightful. But they're describing something independent of us. The Pythagorean theorem would be true in a universe without humans. Right triangles would still satisfy the relationship. Pythagoras' contribution is making that truth accessible to human minds, translating cosmic order into human understanding. That's the mental process. Not creation, but translation. Not invention, but recognition. Looking at tiles and seeing truth.